So I'd like to welcome everybody to our picture language seminar today. We're doing this jointly with the Dublin Institute for Advanced Study. It's their seminar as well. And I think that many people will be interested to hear this talk later. Joel Leibowitz said he's going to rebroadcast the talk on May 7th. So just to give you a little introduction, we have a weekly seminar here at 10 in the morning, and these are the references. This is a picture of our group meeting just a year ago. But if you go to our website, then you will see the Picture Language Project link to go to seminar. And if you go to seminar, you'll see a list of the talks. We have very good talks after Jürg, Daniel Gottesman next week, Roberto Longo, Werner Nahm, Alina Vadiva, Scott Aronson, and Sean Cooey are the next ones. And after the talks, you can go through this link to our YouTube channel. And the first 3 talks we put on YouTube are right there. And after Jürg's talk, that will be there for viewing as well. So today we have Jürg, and we're very happy to have Jürg Fröhlich. He's known for his work in quantum field theory, phase transitions, infrared bounds to study continuous symmetry breaking, work on gauge theory, supersymmetry, quantum Hall effect, and he's also interested in the foundations of quantum theory. So putting those all together, Jürg's ensured that ETH is a leading center for theoretical physics and really needs no further introduction. So Jürg, if you share your screen, you should start. I have to find Jürg. Just a minute, Jürg. Right. There's so many people here. It's hard to find you. Okay, now you're on.
So, all right. So I'm still getting the message that my screen sharing is disabled.
Oh, okay. So let's see if we can do something about that. But I have to find you.
All right. Otherwise,
now you should be able to do it.
All right. Can you see it now?
But I see you, but not your screen. You have to click share screen.
All right.
Now we see it.
Very good. All right. Well, so I'm very happy to join this crowd and talk a little bit. This talk is mostly a review of material that you're supposed to know about. Maybe some of you don't know the history so well, so I'm going to talk a little about the history of these results. And towards the end, I'm trying to outline a few ideas that are more recent and that I have been working on during the past several years. So the bulk of the talk is about the Kochen-Specker theorem that claims that there are no hidden variables, theories that reproduce all the predictions of quantum mechanics. You see here on this first slide, to the left, Simon Kochen, then in the middle, Ernst Specker, and to the right, John Bell. Specker was one of my teachers. He was a logician at ETH, and he taught me linear algebra during the first year of my undergraduate studies. Oops. So here is a little outline of what I'm going to talk about. In order to sort of cheer you up a little bit, I'm going to tell you a story about Specker that I learned from Raoul Bott. And then I will make some remarks about a little known paper of Specker's from the year 1960, where he already basically, states the full-fledged Kochen-Specker theorem, but without details of the proof. Then I will go into the details of the Kochen-Specker theorem and also outline a proof. I will also mention in passing Gleason theorem, which plays a certain role, and the generalization thereof. And then I will conclude the talk with an outline of some more recent ideas on how to complete the mathematical structure of quantum mechanics in such a way that all these, awful puzzles will disappear. I like to call this the fourth pillar of quantum mechanics. Quantum mechanics has been standing only on 3 pillars so far, so it's time to erect the fourth one. All right. So here is a story about Specker's stay at the Institute for Advanced Study at Princeton. That's a long time ago. In the first half of the 20th century, thanks to Heinz Hopf, ETH Zurich was a world center of what Henri Poincaré had called analysis situs, nowadays called algebraic topology. So Specker completed a PhD under the supervision of Heinz Hopf, and then went to the institute at Princeton to spend a little more than a year there. He appeared to know essentially everything of relevance in algebraic topology. At the institute, he met the young Raoul Bott, an electrical engineer turned into a mathematician with an untamed curiosity in algebraic topology. And Bott would come up with a new conjecture about topology almost every day and would try it out on Specker. After Specker had succeeded in disproving several of Bott's conjectures, he proposed a bet. He would disprove every one of Bott's conjectures within 5 minutes. For a while, Specker won the bet, but after some time the situation changed, and as is well known, Bott became a famous topology. Let me tell you a second story, which is also a little interesting because it describes some of the sort of psychology of Specker. Specker and Bott went for a walk in the Institute forests, and it was during the season where there were lots of fireflies. After a while, Bott said, "Isn't it nice to see these fireflies?" And Specker's reaction was, "So you see them too?" Apparently that wasn't understood. Think about what it means. So here is a picture that sort of summarizes Specker's 1960 paper, where he sort of builds upon foundations laid by von Neumann and Birkhoff in order to show that there are no hidden variables versions of quantum mechanics. So this paper is written in a very unusual style. In particular, it contains a little story about a wise man who was in the services of King Asarhaddon and taught at a school for prophets named Arba Ilu. This wise man apparently wasn't very successful as a teacher, but he had a very beautiful daughter. And all of his students apparently were interested in getting married to the daughter. So he thought he should select the right suitor by having them doing a little prophecy about boxes. So he had arrangements of 3 boxes, A, B, and C. 2 of the 3 boxes would always contain a gem or be empty. If you think classically of what the probability is to select 2 boxes that are either both full or both empty, you find easily that the probability is 1/3. So he told the suitors that they should predict which of the 2 boxes were either full or empty. And the problem was that whenever any one of these young men would propose a bet, it turned out that one of the boxes they opened was full and the other one was empty. It just never happened that both of the boxes were empty or filled. So it appeared that whenever the first box, say A, was full, then the second one was empty, which should then imply that the third one was full. But in fact, it was impossible to open the third one. So you can, so in fact, these boxes were quantum mechanical, and the probability for two of them to be either both full or both empty just vanishes. You can reproduce this prediction by thinking of, spin singlet pairs of electrons, and then measuring, say, the Z component of the spin of two electrons. Then one spin is always up, meaning that the detector is filled with a gem, and the other spin is down, which means that the detector is empty. So the point about this story is that the implication that A implies B and B implies C does not mean quantum mechanically that A implies C. That's very easy to see if you think of projections. It can happen that some of these projections do not commute. So, and of course, the point is that in quantum mechanics, you cannot verify three statements simultaneously in general. So that's this story about Sarhadon and his wise man. So let's go on. Well, what's the problem? I seem to have a problem. So the paper that Specker wrote was called Die Logik nicht gleichzeitig entscheidbarer Aussagen. And he starts with a quote of Ferdinand Groncet, La logique est d'abord une science naturelle. And the question Specker proposes to answer is whether you can embed all the statements of a quantum system into a Boolean lattice by enlarging the ensemble of possible statements. And he then shows that the answer to this question is negative, except for dimension 1 and 2. And he claims that there is an elementary geometrical argument that will show why the answer to the question is negative, but he doesn't actually develop this argument in any detail. In fact, the argument was then presented in great detail in the paper by Kochen and Specker. In any event, this first paper dates to the year 1960, so it was definitely before Bell's work. I seem to have a problem now with somehow I cannot. So now this is the problem of hidden variables in quantum mechanics, the paper by Simon Kochen and Ernst Specker from 1967. The question they address is there a hidden variable theory recovering all the predictions of quantum mechanics? Or in other words, can the predictions of quantum mechanics, or the statements about quantum mechanical systems be embedded in a Boolean lattice? So let S be a physical system to be described quantum mechanically. Its Hilbert space of pure state vectors is denoted by H. And maybe I should, just a second. All right.
Jürg, let me interrupt just for a second and say that if somebody wants to make a comment, if you hold down your space bar, then your computer is unmuted and you can talk.
All right. I hope everybody has heard that. So H is the Hilbert space of pure state vectors of a physical system. If the answer to the question proposed by Kochen-Specker were yes, this would imply that there exists a measure space, capital omega, with a sigma algebra F, and maps little f and rho. F maps self-adjoint operators on the Hilbert space H to real valued measurable functions on the measure space omega, and rho assigns to every state vector in the Hilbert space H a probability measure on the space omega F. And the following properties are required. You want to preserve expectation values. In other words, for every self-adjoint operator on the Hilbert space H, the expectation in the state psi should be the same as the integral of the function f sub a with the given with the measure d rho sub psi. So that's preservation of expectation values. Then all right. Then suppose u is a real valued function. It's assumed to be bounded and measurable. Then you want to require that f applied to the operator u of a is the same as u composed with the function f sub a. The requirements P1 and P2 are compatible with each other. That's easy to check. It's an exercise that you may want to do over lunch. And moreover, P1 and P2 imply the following fact. Suppose that M is an abelian algebra of commuting self-adjoint operators acting on H, then the map F that assigns the self-adjoint operators A in M measurable functions F sub A on omega is an algebra homomorphism, meaning that F sub A1 times A2 is the same as the product of the functions F sub A1 times F sub A2. This is very easy to prove in finite dimensions. So here is the Kochen-Specker theorem. So it was already noticed by Specker in 1960 that the hidden variable theory satisfying properties P1 through P3 exists if the dimension of the Hilbert space equals 1 or 2. And you can check this by looking at the quantum mechanics of a spin 1/2 object that nowadays people call a qubit, which of course sounds much more interesting. In the old days, it was simply called a spin 1/2. So here is the theorem of Kochen and Specker, which was published in 1967. If the dimension of the Hilbert space is greater or equal to 3, then a hidden variable theory satisfying P1 through P3 does not exist. So how does I will give you a sketch of the proof. So we consider a particle whose spin degree of freedom is described by a vector operator S acting on the Hilbert space H, which in this case is chosen to be a three-dimensional complex Hilbert space. In fact, S is simply the spin operator for a particle of spin 1. Let N1, N2, N3 be the standard orthonormal basis in R3, and set S sub J to be the scalar product of the vector operator S with the unit vector N sub J. Then, as you can easily find the matrix representations for the components S1, S2, and S3 of the spin operator S. Looking at these matrices, we observe that the operators P sub j given by identity matrix minus Sj squared, where j runs from 1 to 3, are three mutually commuting orthogonal projections of rank 1, and the sum of these projections is the identity. Let's now pass to an arbitrary orthonormal basis in R3. So let's suppose that E vector is an arbitrary vector on the unit sphere in R3. And I define P of E to be identity minus S dot E squared. So this is an orthogonal projection of rank 1, projecting onto the one-dimensional subspace of the Hilbert space H, and by this unit vector E. In other words, the matrix elements of P of E in the basis N1, N2, and 3 are given by P E sub ij equals EI times EJ, where EI is the ith component of E in the standard basis. For an arbitrary orthonormal basis, E1, E2, E3, one then finds that the sum of the P of Ej's equals the identity, and P of E sub I times P of E sub j equals delta ij times P of E sub I. The projections P of Ej, j goes from 1 to 3, are obviously functions of a single self-adjoint operator. Let's call it A. A is given by sum over j from 1 to 3, alpha j times P of Ej, where the eigenvalues alpha 1 is smaller than alpha 2 and alpha 2 is smaller than alpha 3. A generates a maximal abelian subalgebra of the algebra of bounded operators on the three-dimensional Hilbert space H. All right. Now we are going to make a fatal assumption. We assume that there exists a hidden variable theory satisfying properties P1, P2, P3. I hope you still remember them, otherwise we can still flash them once. I seem to have terrible problems transporting my slides. How come? What's... Oh no, it's very strange. Yes. So let's once more look at P1. So P1 was the preservation of expectation values. P2 is that if U is a arbitrary bounded measurable function, f sub u of a equals u composed with f sub a, and 3 is this algebra homomorphism. All right, so these are the requirements, and now this the fatal assumption is the following. There exists a hidden variable theory, namely such maps little f and rho, satisfying properties P1, P2, P3. And we want to show that this is not possible. Now, since P of E is a projection, P of E squared equals P of E. That implies via property P2 that the image of the projection P of E, namely this function f sub P of E, is a characteristic function on the measure space omega. It depends on the unit vector E, but it's a characteristic function. Equation 2, let's see where equation 2 is. Yes, equation 2 then. So yes, equation 2 implies that for an arbitrary orthonormal basis, E1, E2, E3, the sum of the characteristic functions chi sub Ej, j goes from 1 to 3, equals the function 1 on the measure space omega. We assume here for simplicity, in order not to get tied up with little technicalities, that this measure space omega is a discrete set. Well, then for any point omega, little omega in the measure space, capital Omega, we can introduce a certain function phi sub omega of E, which is given by the value the function chi sub E takes on the point omega. I now consider phi sub omega not as a function of omega, but I fix omega and view phi sub omega to be a function of the unit vector E. So what are the properties of this function? It only takes the values 0 and 1. In other words, phi sub omega of E equals 0 or 1 for any unit vector E in the unit sphere contained in R3. That's simply because the characteristic function chi sub E of omega only takes values 0 and 1. If E belongs to any orthonormal basis, namely E equals E1, and then I complete E1 by adjoining two further unit vectors E2 and E3 to an orthonormal basis of R3, then the value phi sub omega of E should be independent of how I complete E to an orthonormal basis. This can be done in many different ways, but phi sub omega of E should not depend on how I choose E2 and E3. And of course, the sum from over j from 1 to 3 of phi sub omega of Ej must be 1. That is simply the statement that these projections P of E sub 1 plus P of E sub 2 plus P of E sub 3 equals the identity. So properties 1 and 2 imply, this is now an important statement, so you should listen carefully. Properties 1 and 2, or I and double I, imply that the function phi sub omega is an additive measure on the lattice of orthogonal projections acting on C3 for every little omega in the measure space capital Omega. So additive measures on the lattice of projections in a Hilbert space were investigated by von Neumann and Birkhoff, and then played an important role in Gleason's theorem that will be recalled shortly. So here is now the geometrical argument that Specker was alluding to in his 1960 paper, but didn't develop in detail. So the evaluation of a function phi sub omega with properties I, double I, and triple I on finitely many unit vectors in R3, which give rise to finitely many orthonormal bases in R3, leads to a contradiction of the following sort, that for some unit vector E, phi sub omega of E would like to simultaneously be 0 and 1, which of course it cannot do. So in fact, for one way of completing E to an orthonormal basis, you conclude that phi sub omega of E should be equal to 0, and for another completion of E to another orthonormal basis, you conclude that phi sub omega of E should be equal to 1. This is something that people call contextuality. So the value of phi sub omega of E apparently depends on context. Now, Kochen and Specker have found an explicit construction of finitely many unit vectors in the unit sphere S2 that lead to this contradiction. By now, apparently the best variant of their construction requires only 18 different unit vectors. I haven't checked this, but that's what is claimed in the literature. Now, to construct these configurations of orthonormal bases in R3 is a little tricky, and it's not so easy to visualize what's going on. But there is a very abstract argument that shows why functions phi sub omega with properties 1 through 3 cannot exist. And here is an abstract proof of this fact. It is based on Gleason's theorem. And in fact, I have learned this argument from Norbert Straumann, who was a colleague of ours at the University of Zurich. So it goes as follows. As I mentioned before, property 3 says that the function phi sub omega is an additive measure on the lattice of projections of the Hilbert space C3 for every point little omega in the measure space capital Omega. Gleason's theorem then says that there exists a density matrix capital phi sub omega, which is a positive matrix whose trace equals 1, such that the function little phi sub omega of E equals the trace of this density matrix capital phi sub omega times the projection P of E, which is the same thing as the expectation of the density matrix phi sub omega in the vector E. But it's very easy to see if you fix the density matrix phi sub omega, you always find a unit vector for which little phi sub omega of E, namely this expectation of capital phi sub omega in the vector E, takes a value that is strictly positive and strictly less than 1. But this contradicts property 1 of the function little phi sub omega. So that means that such functions do not exist. And that completes really the proof of the Kochen-Specker theorem. Now, I remark there is an amusing connection with Kakutani theorem, which I sort of discovered by browsing through the literature some time ago. And it has something to do with Freeman Dyson, who just died recently. And so it's worth recalling this connection. Gleason's theorem that we had before, this fact that phi sub omega of E is given by the expectation of the projection P of E in the state given by the density matrix capital phi sub omega, this function is obviously continuous in E. So let us consider an arbitrary real-valued continuous function phi on the n-dimensional sphere Sn centered at the origin. Dyson's variant, which he published in the Annals of Mathematics in 1951, of a theorem of Kakutani, says that there exist n+1 points, x1, x2, up to xn plus 1, on the unit sphere Sn, such that the n+1 unit vectors Ej given by connecting the point xj to the origin are mutually orthogonal, and the function phi takes equal values on all these n+1 unit vectors. So this, of course, immediately, so if you know that phi sub omega is continuous, you immediately find a contradiction to properties I and double I of the function phi sub omega that we had assumed. All right, well, that's this connection with Kakutani theorem. Now I want to make a few remarks. If you go through these proofs of non-existence of hidden variable theories, you find out that all these theorems are sort of based on the obvious fact that there doesn't exist a homomorphism from a non-commutative algebra into an abelian algebra. Mermin's version of the Kochen-Specker theorem makes this particularly clear. In fact, in some sense, I don't like Mermin's version very much because it sort of makes the whole enterprise look a little trivial, actually. So that's the remark one. Now, okay, remark two. And that's of some significance. Gleason theorem was originally proven for finite dimensional projections acting on a separable Hilbert space. However, you can actually generalize Gleason theorem to additive measures on the lattice of orthogonal projections of a general von Neumann algebra. So you could replace the algebra of all bounded operators on a Hilbert space by a, say, type 2 von Neumann algebra, or even by a type 3 von Neumann algebra. And Gleason theorem is still true. It says that if you have an additive measure on the lattice of orthogonal projections in a general von Neumann algebra, then this measure is given by a normal state on the von Neumann algebra. I will come back to this generalization of Gleason in a few minutes. But before I do that, let us also briefly review what Bell's inequalities have to say about the non-existence of hidden variables theories reproducing the predictions of quantum mechanics. Of course, Bell's inequalities have become much more well-known than the Kochen-Specker theorem because they are more quantitative and can be put to experimental tests. So let's see what they tell us. Let us consider correlations between the outcomes of some family of commuting measurements on two causally independent systems. Let's call them A and B. In other words, I can do measurements on system A and measurements on system B simultaneously, and they commute. So it turns out that if you look at quantum mechanical correlations, so you measure some observables A1 up to AN in system A and observables B1 up to BM in system B, and then you look at the correlation matrix expectation of A sub I times B sub J, then that's a correlation matrix. Let us shrink all the matrix elements of this correlation matrix by a certain fixed constant K sub G inverse, which is smaller than 1. Then the resulting matrix lies inside the range of the corresponding classical correlations. What are the classical correlations? You replace the observables A1 up to AN by functions on a measure space, and B1 up to Bm also by functions on the same measurement space. And then you look at integrals of the function A sub I with the function B sub j times the function B sub j over the measure space. That's a classical correlation. That's the matrix element of a classical correlation matrix. So it turns out that when you multiply all matrix elements of quantum mechanical correlation matrices by a constant Kg inverse that is smaller than 1, you get a matrix that is inside the range of the corresponding classical correlation matrices. This is something that Zirlsen proved. Zirlsen died recently. In fact, I was supposed to participate in a memorial meeting for Zirlsen in Israel, but of course it has been called off because of the coronavirus. Now this constant Kg takes the value approximately 1.782, and it is called Grothendieck constant, because Grothendieck introduced it in his theory of tensor products of topological vector spaces. So I think that's a very interesting observation that Zirlsen made. Now, you might argue.
Is this a physical interpretation of Grothendieck's constant?
When you go to through the proof, which is a little lengthy, I cannot possibly reproduce it, you see that this Grothendieck constant appears very naturally in discussing these quantum mechanical correlation matrices. If you like, I can send you a proof that I once adapted from the literature. It's maybe about 5 pages. It's definitely too long to be reproduced in this talk, but I would say the proof shows that this Grothendieck constant has a good meaning in this context. Now, of course, you might argue that perhaps this is a pessimistic theorem, that in fact the range of quantum mechanical correlation matrices is contained in or equal the range of classical correlation matrices, but we know that this is not the case. That's what Bell found out in his work of 1964. He showed that the range of quantum mechanical correlations is strictly larger than the range of the corresponding classical correlations. And I will show why this is so by just going through a very well-known example that Clauser, Horn, Shimoni, and Holt worked out. So we look at the Hilbert space that is the tensor product of 2 complex Hilbert spaces of dimension 2, one for system A and one for system B. So you can think of systems A and B to be just spin 1/2s, or qubits. All right. So here is the Clauser, Horn, Shimoni, Holt version of Bell's inequality. Let's pick a maximally entangled state in the composed system, A composed with B, and it's given by the spin singlet state. Nowadays, people call it the Bell state. Let's call it capital psi. It's given by 1/√2 of spin up for A tensored with spin down for B minus spin down for A tensored with spin up for B. We define a certain correlation matrix E by setting E of E1, E2 is the expectation of an observable A sub E1 multiplied by an observable B sub E2 in the state capital psi. Now, A sub E is the vector of Pauli matrices dotted into the unit vector E, tensored 1, and B sub E is 1, the identity matrix, tensored the vector of Pauli matrices of system B dotted into E. It is easy to calculate this expectation of A sub E1 times B sub E2 in the spin singlet state capital psi. It's an exercise that takes you a minute or so. You find this expectation is minus E1 dot E2. All right. Now I consider the following combination of correlation matrix elements. It is called, it is denoted by F of E1, E2, E1 prime, E2 prime. And it is given by capital E of E1, E2 plus capital of E of E sub 1 and E prime sub 2 plus capital E of E1 prime, E2 minus capital E of E1 prime, E2 prime. So E1, E2, and E1 prime, E2 prime are 4 unit vectors. It is important that A sub E1 does not commute with A sub E1 prime, and B sub E2 does not commute with B sub E2 prime for a reason that I will explain. So, if there were a local hidden variables version of quantum mechanics that would assign to the A sub E's functions, little a sub E's on a measure space, and to the operators B sub E functions, little b sub E on the same measure space, then you would find that this object capital F would have values that are contained in the interval from -2 to 2. No matter how you choose the unit vectors E1, E2, E1 prime, and E2 prime. This is a little exercise that I'm not going to do for you. It's really just a numerical inequality for 4 real numbers, all of which are contained in the interval between -1 and 1. Now, if you choose your unit vectors E1, E2, E1 prime, and E2 prime appropriately, and then use equation 7, namely that in quantum mechanics, the correlation matrix capital E of E1, E2 is given by -E1 dot E2, then you find that this object F of E1, E2, E1 prime, E2 prime takes the value 2 times square root of 2, which is definitely much larger than 2. And so this shows that there cannot be a local hidden variables version of quantum mechanics. This prediction 9 has been tested experimentally, and the most well-known experiments in this respect are those of Alain Aspect. They were then reproduced and made more precise, for example, by Nicolas Gisin in Geneva. So in other words, apparently it has been shown that nature, which we believe is quantum mechanical, violates Bell's inequality 8. All right, so that's the review of Bell's inequalities. So you see, it is of course of interest to know that there are no hidden variables theories that reproduce all the predictions of quantum mechanics. I think, in the 60s, this was an important insight because people had become a little disenchanted with von Neumann's no-go theorems. And so these, the theorems by Kochen-Specker and by Bell certainly were much more convincing than von Neumann's analysis. Of course, then there was the Bohmian mechanics, which in some sense is a counterexample to these no-go theorems. However, the problem is that Bohmian mechanics does not reproduce the entire lattice of projections on the Hilbert space of a system. And so in that respect, it's not a full-fledged hidden variable theory of quantum mechanics. Anyway, I think we have all come to accept the fact that it is impossible to reproduce all the predictions of quantum mechanics by using commutative hidden variable theories. I find this, mildly interesting, but it doesn't, unfortunately, solve some of the real conundrums of quantum mechanics, such as the measurement problem. And so I would like to sketch a few ideas of how to actually solve things like the measurement problem. The problem with, Kochen-Specker and Bell is that they don't talk about time, they don't talk about events or measurements, they don't talk about the evolution of physical systems. And so we have to add these concepts in order to come up with a more full-fledged presentation of quantum theory. So let's briefly recall how the quantum theory of an isolated open physical system is developed. What is an isolated open physical system? An isolated physical system is one that for all practical reasons has negligibly small interactions with the rest of the universe. What is an open, isolated physical system? It is a physical system that is isolated and can release modes that speed away at the limiting speed. So in practice, these would be photons that speed away at the speed of light, or gravitons, or also zero mass modes. You can also develop a theory of open isolated physical systems that is non-relativistic. Then the limiting speed is infinite, and the modes that the system can release are modes that speed away at infinite speed. This, of course, introduces somewhat pathological properties, but that's how it is. So let's now give a mathematical definition of an isolated open physical system S. It is described by a descending filtration E greater or equal to T of von Neumann algebras. Little t is time. The von Neumann algebras are denoted E greater or equal to T. These von Neumann algebras are generated by all possible events that might happen at time t or later. Events will be described by projections. And the point is that if you have an isolated open physical system, namely a system that can release modes that speed away at the limiting speed, then these von Neumann algebras E greater or equal to T are sit inside each other in a proper way. Namely, if time t prime is larger than time t, the von Neumann algebra generated by all events that can happen at time t prime or later sits properly inside the von Neumann algebra E greater or equal to T generated by all events that can happen at time t or later. In fact, the relative commutant of the algebra E greater or equal to T prime inside E greater or equal to T tends to be an infinite dimensional non-commutative algebra for realistic models of nature. Now, I have introduced the notion of event. I represent events by projection operators, and the importance of having a clear notion of events was, of course, emphasized by Rudolf Haag. And he wrote several papers trying to sort of come up with a theory of events, but unfortunately he couldn't quite complete the job before he died anymore. But his papers are definitely worth studying. So potential events possibly happening at time t or later are here represented by the lattice of orthogonal projections inside these algebras E greater or equal to T. 2. What are states of an isolated open physical system? There are additive measures on the lattice of projections in E greater or equal to T, and thus by the generalization of Gleason's theorem, they are given by normal states on these von Neumann algebras E greater or equal to T. So we now know what isolated open systems are and how to describe them. We know how to describe states of such systems. Now we should also understand how to describe time evolution. And Heisenberg, who had a much clearer idea of what quantum mechanics should be about than Schrödinger, a much clearer idea, at least physics-wise. He said time evolution should be formulated for operators or for observables. And how does the time evolution of operators look like? It is given by conjugation of the operators with the unitary propagator of the system. This time evolution acts on the algebras E greater or equal to T simply by shifting the subscript T. All right, and so we have these pillars 1, 2, and 3 of quantum theory, and here is now a 4th pillar. So, given a state omega on the algebra E greater or equal to T, we say that an event described by a partition of unity given by a family P of T of two disjoint orthogonal projections in the algebra E greater or equal to T actually happens at time T or later if PT, if this family of orthogonal projections generates the center Z sub omega of E greater or equal to T of the centralizer C sub omega of E greater or equal to T of the state omega on the algebra E greater or equal to T. The notion of a centralizer of a state on an algebra is a very natural notion that you know from group theory. The center of the centralizer simply consists of all operators in the centralizer that commute with all other operators in the centralizer. And so if we have a state, we can in principle, on the algebra E greater or equal to T, we can in principle compute Z sub omega of E greater or equal to T. If this is an algebra that has at least two elements in it, then it is non-trivial. And an event happens if at least two of the projections in Z sub omega have a strictly positive Born probability in the state omega. What's the Born probability of a projection? It's simply the expectation value of the projection in the state little omega. So this point 4 introduces an idea of what an actual event is in quantum mechanics. Now you have to supplement the standard formulation of quantum mechanics by the following assumption or postulate or axiom. Suppose you have a state omega on the algebra E greater or equal to T of possible events happening at time T or later. Then if an event actually happens at time T or later, the state of the system right after time T is given by one of the states omega sub pi, where pi belongs to the center Z sub omega of E greater or equal to T and has a positive Born probability, and the state omega sub pi is simply given by the state omega of pi x. Pi x is an operator normalized to assign expectation 1 to the identity. So it's this equation 11 that defines the state omega sub pi. So the probability that pi selects the state of the system right after time t is of course given by Born's rule, namely by the expectation of pi in the state omega. These 4 points that I have formulated, one, what is an isolated open system, and in particular this principle of diminishing potentialities, which is this equation 10, 2 states of the system, and 3 Heisenberg time evolution, and 4 the definition of actual events, including the axiom of the state collapse. These 4 pillars give rise to a fundamentally stochastic time evolution of states in quantum mechanics. In other words, you see, it's a mistake to believe that states in quantum mechanics evolve according to a Schrödinger or Schrödinger-Liouville equation. They in fact evolve according to a stochastic time evolution that is completely determined by the 4 points that I have summarized above and this state collapse axiom. This is a new type of stochastic branching process that in fact mathematicians unfortunately have not analyzed yet. In fact, I'm in the process of writing a little paper about a concrete model that exemplifies all these things. And the model has the charming feature that the time evolution of states smoothly interpolates between unitary Schrödinger equation and the Markovian Schrödinger evolution and the Markovian evolution of states. The question is, what makes the evolution Markovian? Well, it's the entanglement of the state of the system with the modes that it releases and that speed away at the limiting velocity. So the larger the entanglement, the more Markovian the evolution looks like. All right. So this discussion should convince you, if you have understood it, which I do not assume, that quantum mechanics is intrinsically probabilistic and irreversible. This description of time evolution introduces a natural dichotomy between past and future. The past is a history of events, of facts that have happened, and you can monitor them. I did not tell you how to monitor events. I would go a little beyond the time I have. While the future is an ensemble of potentialities, the future is described by events that might possibly happen, but may not happen. The particular completion of quantum mechanics that I've outlined here, in particular items 1 and 4, is quite recent. I think it provides a very natural solution to the so-called measurement problem, and it establishes a fairly natural ontology for quantum mechanics. I like to call it the ETH approach to quantum mechanics. E stands for events, T for trees of states, and H for histories. A history is a certain path on the tree of possible states of a system. It is the only consistent so-called interpretation of quantum mechanics that I know about. Well, here is a remark. Well, maybe I think I'll leave this out. There's a remark about Hua Xin Lin's theorem on almost commuting self-adjoint operators. Anyway, I think it's time to close. Quantum mechanics remains a great source of interesting and inspiring mathematical problems, that's for sure. And I would like to, here incidentally are some metaphorical representations of the quantum mechanical time evolution. The green tree is the tree of possible states. The branching points are the events, and the blue path is a history, namely a sequence of events a system has gone through. That's an illustration of the dichotomy between past and future. And so here is, here are some pictures that you might enjoy. This is a little known Swiss theorist. This is Specker in his young years. This is Simon Kochen in his young years. And that's how we looked like relatively recently in Arthur. It was 2009, right?
Right, exactly, in June.
So this picture was taken by Arthur on the balcony of my apartment in Zurich during a dinner attended by Ernst Specker and Simon Kochen and Arthur and myself and one of their Spanish friends. All right, so I thank you. This is the end of my talk. And of course, I'm happy to take questions.
Well, thank you, Jürg, for a very beautiful talk. And it raised a lot of questions. And I remind people that to temporarily unmute your computer, press this and hold the space bar, or you can click on the unmute icon. Who has a question?
May I ask a question?
Yes, Roberto.
Jürg, you assumed that centralizer is non-trivial.
Yes.
But we know that in many physical systems, the centralizer is trivial.
Well, unfortunately, those are systems which are unphysical in the sense that they don't produce any events. You see
But
that?
they are physical. Any time you have a thermal state, which is ergodic, then you have trivial centralizer, for example.
A thermal state I call passive. It does not produce any events. if you have a state describing an isolated system that is perfect thermal equilibrium, nothing happens. You don't see anything happening. In order for something to happen, you have to join this system to another system that is not in equilibrium. You see, and then of course events may happen. So the example of equilibrium is one that is well known to me, and in fact there is a little story about passive states. Passive states are ones that for which the centralizer of these states is the same as the center of the algebra, and so nothing interesting happens. Okay. Thank you for the question. I hope my answer was more or less clear.
Can you tell us what Lin's theorem is?
Oh, would you like to know what it is? This, yeah, right. Let's, oops, no, something happened that I did not want. So, you see, Lin's theorem is the following theorem. You have a bounded operator A and a bounded operator B. Let's suppose the norms of A and of B are smaller or equal to 1. Let's suppose that the norm of the commutator of A with B is very tiny, smaller than some epsilon that is maybe 10 to the minus 7 or so. Then the theorem says that norm close to A, there is an operator A tilde, and norm close to B, there is an operator B tilde, such that A tilde and B tilde commute. That's the theorem. There are many different proofs. One of them, for example, was proposed by Matt Hastings. It wasn't quite right, but then I guess Mrs. Ogata corrected it. But there are many other proofs, also a Russian proof, which is very nice. I forgot the name of the authors. This theorem should have the following generalization. Suppose you have a von Neumann algebra M, and a normal state omega in M. And let's suppose you have an operator X inside this von Neumann algebra M with the property that the adjoint action of X on the state omega is a linear functional on M that has a very tiny norm. Then we would be tempted to conclude that norm close to X, there is an operator X tilde, norm close to state omega, there is another state omega tilde, such that add X tilde applied to omega tilde vanishes. In many special cases, this can be proven, but I do not know a general proof of this fact. In fact, I was asking this question to Roberto and to you, Arthur, in Bonn at the Hausdorff Center. When was it? 3 years ago?
I remember, yeah.
Yes, and I also asked Detlef Buchholz, and unfortunately so far I have not gotten any general answers. The special cases I've worked out by myself, but the general answer I don't know. I think it's an interesting problem.
So Werner Nahn has a question.
Yes. A while ago, Sorkin wrote a paper stating that the Copenhagen interpretation of the measurement process violates relativistic causality because if you have an instantaneous collapse, then you can use it to transmit information from one end to the other end of the region you control faster than velocity of light. Shortly before Christmas, 3 of our fellows wrote a paper looking at that in more detail. So what about the ETH interpretation of quantum mechanics?
So, I mean, formulated in the generality, you have formulated it, I think it's simply wrong. I think it's wrong what you said. But you see, I have tried to formulate the ETH approach in a relativistic way. In fact, I've published a paper, you find it on the archive. And I mean, of course, this is, ongoing work. I'm not claiming that I understand every detail, but I have not encountered any problems so far. It just looks perfectly good. I have no problems. In fact, the ETH approach, you see, there is an interesting fact. When you look at models that realize all these properties, 1 up to 4 of the ETH approach, in a non-relativistic context where the speed of light is infinitely large, you always find that the Hamiltonian generating the time evolution of such systems is unbounded above and below. If it is bounded below, no events happen. So if you want to have a non-relativistic system that features events, you need a Hamiltonian that is unbounded above and below. But relativistically, you don't have this problem. A relativistic incarnation of this ETH formalism actually is compatible with a Hamiltonian that is bounded below. This is based on work of Detlef Buchholz and the late John Roberts, who analyzed QED and showed that in QED, this postulate, postulate 1, this descending filtration of von Neumann algebras, this postulate becomes very natural in a relativistic quantum field theory with massless modes. So that's the work of Buchholz and Roberts.
Thank
So
you.
in other words, I believe everything is just fine, based on my knowledge. If you want to know what the precision by which these things are known, you should look at my paper. Are there any other questions or comments?
I think Peter Love has a question.
Hi, yeah, thanks for a very nice talk. I just wanted to clarify whether the addition of this 4th axiom gives you a theory that's empirically equivalent to regular quantum mechanics. Because the idea of using actual events or events that actually happen makes me slightly worry there might be an intrinsic decoherence mechanism.
I didn't quite understand what you said. There was some technical problem.
Oh, sorry.
Could you repeat?
Sure. Is this extension of quantum mechanics empirically equivalent? Or do you introduce is there a possibility of an intrinsic decoherence mechanism by having these actual measurements that happen?
So you see, one of the things that I always found perplexing is that people believe they know what quantum mechanics is. Since quantum mechanics has been plagued by various sort of puzzles, it suggests that we don't know what quantum mechanics is. So I'm proposing a completion of the standard quantum mechanics, and the basic novel idea that, in some sense is very simple but has not been pursued before is this principle of diminishing potentialities, which means that at some, if you haven't paid attention up to time t, then unfortunately have missed certain things, namely everything that you might see after time t is strictly less than what you could have seen if you had started to do your observations earlier. That's the meaning of this equation 10. And of course, this equation 10, together with the idea of entanglement, immediately clarifies why events might happen, why these centralizers, C omega, that I'm introducing in 4 might be non-trivial. Does that answer your question?
Well, let me ask you in a different way, which is, do you think there could be a system or an experiment where if I did calculations with the first 3 axioms,
yes,
the different result from whether I did the calculations with the 4 axioms.
Well, I don't know what you want to calculate. What do you want to calculate? If you want to calculate the evolution of the state of the system as time goes on, you cannot avoid using axiom 4 or postulate 4, using this collapse postulate. If you don't use it, you get the wrong prediction for how the state of the system evolves.
Okay, thank you.
This is really discussed in some, well, in fact, I have given a course about all these things at Ludwigs Maximilians Universität in Munich. It was 2.5 weeks long. I had to teach 2 hours per day. It was pretty heavy load. And there are notes of my lectures that you can download from the website of LMU. And in those notes, you find all the details and enormous discussions of examples and so on and so forth. So whoever wants to understand some of the details will find them in those lecture notes. Summaries, shorter summaries are contained in 2 recent papers that you find on the archive. Any other questions or comments? Maybe not.
Well, if there are no other questions, then I want to thank you, Jürg, for absolutely wonderful talk, which it's interesting to see this reformulation of measurement theory and quantum theory. And it would be nice to see this paper that you're talking about where you can reformulate quantum field theory in this framework.
Oh yes, well you find, you see, you find a short summary on the archive. The paper is called Relativistic Quantum Theory. And if you want to have more details, you should look at these lecture notes of my course that I taught in Munich. Of course, this is not finished. I'm still working on, in fact, I'm just trying to write 2 further papers. One about particle tracks, why particles moving through a, say, bubble chamber leave tracks that look like classical trajectories. It's an old, well-known problem that was posed by Mott, and we finally believe we understand what's going on there. And the other one is I'm trying to write a paper about a non-relativistic model, a very concrete model that illustrates this, these 4 properties of the ETH approach. So, but that will take a little time. You have to have some patience before you will see it. All right, well.
Just one very small question.
Yes.
This is Dinjo O'Connor from Dublin. And thanks for giving the joint seminar to us as well. We piggybacked in on this. There are other treatments of open systems. Now, and I'm just wondering, how different is this treatment going to be to something like the Feynman treatment of open systems?
Whose treatment?
I think Feynman and was it Vernon that had a treatment of open systems?
Well, you see, if you read through Feynman, you will never find anything like this property 10, which I call the principle of diminishing potentialities. It's a totally crucial fact of life in order to understand how events can happen and how measurements can be done. That's definitely, I think, unfortunately not in any of these old papers. I'm not sure that I can say much more than that. I believe there is a little bit of novelty in this discussion, and people have to get used to it. I got various comments. A few, for example, Joel Leibowitz's friends at Rutgers, such as Shelley Goldstein, he likes it. He thought it was important. But I also got the message from a lady who said, it looks as if it was all nonsense and people as old as I should better go fishing rather than produce research. Now,
You had another comment.
I actually believe it is not so bad, you know. I think this has some value. And of course, it's important to come up with concrete models, but in fact, by now I do have very concrete models. It just needs to be written in a nice way. But the model is already treated in my lecture notes of the course I taught in Munich.
Okay, look forward to seeing that. Okay, thank you.
All right. So,
Werner, do you have another comment?
No. I just want to thank Jürg, and I unmuted to clap my hands.
okay. Well, it was a pleasure to hear you and see you. And Tom, since I see you, maybe we should Skype on what would be a good day? Friday?
Yes, that would be great, Jürg.
Friday afternoon or evening?
Yeah, Friday or the weekend if that's good for you.
Anything is fine, yeah. Before Friday.
Very nice talk. I enjoyed it.
Very nice, very nice.
So let's all unmute and thank Jürg. Thank you very much.
Thank you, Jürg.
Also for organizing this. It keeps us connected and it keeps us motivated, and it's just a pleasure to see you all. So
Thank you, Arthur.
Likewise.
See you again next week.
All right. Bye-bye.
Bye.